Good afternoon, everyone. My name is Ming. I'm working for U.S. Navy NAVFAC EXWC in the Southern California, between the Port Hueneme, between the Los Angeles and Santa Barbara. And I have a co-author, Professor Yue Li, is from the Case Western Reserve University. We team up to do something about the resilience on the non-stationary extreme design load due to climate change for coastal concrete structure. Basically, my project is more broad for the Navy facility. For this particular conference, I just focus on more on coastal concrete structures. The motivation why I'm doing this, the first is ACI 348 Structural Reliability and the Safety Committee will focus on the effect of climate change on structural safety and the resilience of structure and the infrastructure system. I'm the chair of that committee, so I want to try to promote this awareness of this committee, and we're doing the whole reliability, ASC 7, load combination, all kind of things put in design code. Another thing I just mentioned is ASCE, American Society of Civil Engineering. Now, just last month, February 2023, signed an agreement with NOVA to work toward climate-rated infrastructure where NOVA will provide their data. So they will come in the new version and the ASCE 7 or other manual doc will consider climate change. Currently, we do not have anything in the design code. Finally, there's a lot of interest in this climate change and the infrastructure resilience of the planning due to the climate change. Basically, I'm saying is there's a lot of research funding where chase those money, and we start from there. So today's presentation will come from backwards. First, we talk about the coastal concrete structure. What we am talking about for my project, basically for the Navy. Also the damage of the concrete structure by extreme weather. There's one slide. And we'll focus on the extreme design load in ASCE 7. Basically talk about the wind load, storm, and the flooding. We basically, for structure-wise, we talk about the flow velocity because that will cause the damage of your structure. Sea level rise, of course, has been studied a long time. And then we talk about in the design code, how we will model the PDI probability density function we're using and the load combination with this very general idea. I'm not going to do the more detailed study. And then the non-stationary climate change, because non-stationary, that means the historical data cannot be directly applied for the future prediction because climate change, everything changes. And finally, I have two more slides, talk about the resilience and the risk mitigation and the summary, and one slide on the future need. Okay, coastal structure, concrete structure, we'll talk about first building. Everybody work on building. And the parking lot and the road is infrastructure, network, or whatever we talk about. More particularly, what I want to say for the U.S. Navy, we talk about PERS with the piers and the dry dock. It's kind of very important facility for us for the maintenance of the aircraft carrier or submarine. So we are running some issues. We are short of the facility. And so when we look at those facilities, we look at the structure type. And most of the piers are founded by the pile support, which is concrete, cylinder pile, H pile, steel H pile, and pipe pile, steel pipe pile supported. And the water height typically 550 and 40 or 50 depth. For the dry dock, you just see the dry dock is similar like a dam or retaining wall. So there's two different kind of structure we're dealing with that. I put the red mark extreme water level. This is very important design factors And for our pier design or even the dry dock design, there's a specification. This is subject to climate change because in this one, they are including the tide, storm surge, or sea level rise. All the number will be included. This will be the focus on my research and see how we specified in the design code which one we're doing and what's the current practice people are doing here. Damage of concrete by extreme weather. You can find this online everywhere, thousands of photos, but you couldn't find this 6 because we took by ourselves. This 2005, almost 20 years, I was in Hurricane Katrina. I was there, that's the first one. And we have experience, the first-hand experience, how the hurricane to damage your structure and along the coast, restaurant and residential or other apartment buildings. And in 2007, my co-author, Professor Yue Li, also went to Puerto Rico and did a survey, see how those damages. We're not going to go to the detail for this one. Right now, when you look at the coastal area, many people develop the damage curve, probability of hurricane damage curve. You see the vertical is probability damage, and the horizontal is the wind load. Basically, say what's the maximum extreme wind load you have. Then you define your damage level. The first one will be minor damage, is a black one, and the pink one will be medium. Depends on what your definition, you have a curve. For example, this one, if your wind load, the max extreme wind load less than 60 miles per, 80 miles per hour, you really don't have many the damage, don't worry about that. If you over like 160 miles, and you probably got some damage. The degree of damage depends on the condition. Like Florida, the hurricane season is always around the 140.80, that's a range. So we're not going to detail this. So we'll focus on this effect of climate change on the structural performance. So what's the general temperature effect? Because we have buildings, you have expansion, the whole deform, because extreme hot temperature in the summer and the cold temperature in the winter, like Alaska, they will affect your deformation of your buildings. And the wind load, of course, that's the wind load and the hurricane, storm surge, that's blue. I had highlighted blue is one most important design factor in my research focus on. And the flooding and the report. In the flooding, we basically look at the flow velocity because flow velocity will damage your foundation with scour, and that's the parameter we need to look at it. Finally, as mentioned, the sea level rise and the slow load, and this in particular in the North Alaska, Northeast American, there's a lot of study by the U.S. Army Corps of Engineers, see how those data to support future do that. Particularly, we'll talk about the climate change on the coastal country area that I mentioned, the piers and the wharf or the dry dock. First, there's effect of climate change over two parts. One is load effect, another is capacity. When we talk about structural safety, basically we compare your capacity minus your load effect. That's two parts, and the station-bounded probability beta of failure or reliability beta number we control. 3 parts, that's all we talk about structural safety. The first, how does climate change to affect your design node for piers? The sea level rise, give you an example, because we have piers fixed elevation. If water level go up, you have the vessel. Vessel has the cable, we call the mooring system tied with the piers, the bollet. Did you see that? So the load transfer, because the vessel is moving, if you're doing the hurricane, it's moving much. And so those load sea level rise give the angle the difference. They will change the loading condition. That's one. Increased load and wave load, that of course affected by the climate change. And now the question is, Right now, AS7 has a chapter to talk about tsunami. So if we design for tsunami, it's really satisfied with storm surge, because we don't assume this is happening at the same time, right? We design for that, just like we design for earthquake, it's good for the tsunami. So this is a question we need to answer, and in the design code, we do not have an answer yet. And the load effects of the, due to the longer piles, once again, is the sea level rise. Typical, the pile depth, water depth is 30 or 40, 50 feet right range. So if your sea level go up to 5 feet, then you basically 10%, 30%, your loading effect, because the load is like a bending moment, yours L squared. So it's very easily double to this one. So it's, don't think about I just raised the 5 feet, doesn't matter, because comparing your whole loading things, you really double your demand. So another side is actually the deterioration part. The deterioration part, because the CO2 concentration or all environmental temperatures will affect the deterioration rate. However, keep in mind, it's not always bad. Climate change, something will do good things for your structure. For example, if you have a heavy rainfall, it's just the rainfall wash your bridges, and your actually corrosion rate will be slower. And this is the data to support that. So when we talk about climate change, don't think it will be just the bad things, okay? So this briefly to talk about that. And now we focus on the three parameters: wind and flow. Today's presentation is just the wind and the sea level rise. I didn't do the flow velocity because time limit. This is very, if you do a structural engineer background, this is very similar. The left-hand side, how you calculate the wind load, and all the parameters over there. Probably on the right-hand column, the extreme value one distribution, you're probably not familiar with those. That is behind the scenes. Behind the maximum 50 years load, the mean value ratio coefficient, that's what we're looking for. The wind load statistical number is whatever parameter in your equation, we all have look at the mean value standard deviation. So in the ACS 348 committee, we are structural reliability background. We've been doing that 20 years, 30 years. And that's all we are our work. Our end product come out to the load combination, 1.2 that load, 1.6 light load. But most people don't understand where they come from, and misunderstanding why 1.6 load factor for the wave load. People say, my wave load is much larger than the nominal. It's not the same concept. So that's why I want to clarify, and just for the general information to look at those. Once again, this is the design note for each parameters. We have a different data set. We have a different number from, look at the bottom, from some Australia building handle code, and other reference, and different country, different, even the ASC 7, we did the calibration, ACI 318. This building code being calibrated by Professor Andy Nova, which is in my committee, and he's around here, 2003, it's about 20 years ago. So we do have the calibration for this loading, and we can do the order for the extreme loading part. Okay, so this is one just general what we have today. Later on we'll talk about the non-stationary, what are we going to do for the future. And now extreme water level, I mean it's very important. So this include tide, storm surge, and the sea level rise. And for the tide data, we have NOVA. That's why ASC team up with NOVA. They have years data, and we try to use data to come out what the future weather look like. Storm surge has a very good, large variation. Those things maybe dominate what you can do and your final result, but the uncertainty is not happening every day. It's just very extreme event. That's what we'll talk about. And the sea level rise, that's what we'll talk about the sea level rise. We have a different the climate change IPCC code, the International Panel of Climate Change, they make the scenario, 5 scenario. It's good in the control the carbon emission, and it's very typical when you do the climate change. In the base those scenario, you have a global sea level rise range 0.2 to 2 meters by year of 2100, which 90 years, 80 years from now, but they started in 1992. It's huge variation. Once again, this is global. It's not applied to anywhere, it's just some model come out global. It's huge variation. All the factors, I highlighted the blue here. Here, the slide I show you the 5 on the left-hand side, the different variation. The horizontal is the year, and this sea level rise based on the standards. And the right-hand side top is the definition of the extreme world level. This comes from the report, very nice report. I should put the reference there. And the bottom one I show you, and if global scenario is 2 meters, which is the worst case, and by the 2065, I've read minus 1.6 to 0.9. That's based on the different location. So you could be very big variation. U.S. Army Corps of Engineers has an online tool. I highlight this one. They can put your location. They will tell you what's the sea level rise. There's a lot of research to do that. Now, in the practical, people, the UFC is a unified facility criteria used by the military, U.S. military. It's similar like IPC code. In the National Building Code, we have a copy of, code only applied to the DoD standards. In UFC code, very simple, 2 methodologies. The first one on the left-hand side, did you see is some level added up 2 or 3, 2 feet or 3 feet, depending on the location. This is super simplified level. How accurate, we don't know. And another method is the blue one on the left side is Army Online tool. I mentioned it. There's a DoD regional sea level rise, changing and extreme water levels. You can run this program and get what the number. So now my research work is to look at uncertainty of this number, where it's come from, and that's all my project. It's an ongoing one. I just started, probably have a couple of years. And once again, I see the 2 meters is global. It's not going to apply to anywhere. This regional is very important because, for example, give you an example, we have the shipyard, maybe shipyard in some island. Okay, in this island, the situation is different than FEMA flooding the map because all the assumption is behind. So the one study, the same island we did, the other people, not me, did is the yellow one, YK01, you see the bottom one. That's 2 locations with the FEMA map to cover. But we did additional T1 to T6, so we come up with a different number. We report to the FEMA 2017, we got approval. So in that location, and particularly the shipyard, we can use those lower or the different number. So the bottom line is don't just take any number from the FEMA, the map. Of course, simplify you can take, just like a seismic map, you can take it. But for a particular one, if you want to do better or some reason, you have to do that. Regional effect is really, really important. You will change everything in the, particularly this is an island. The island because of water around it. It's not a FEMA model they're looking for, the detail about that. This slide is about the load accumulation. So this is a general rule about the load accumulation, and it's used to be in the ASCE 7 code since 1980s. Everybody right now is like, we have a different methodology, but we don't use it. Current design code, ASCE 7, using this one. Did you see I want to focus on the figure. Don't go to that equation, that too. So that load always there. And then we have a live load. The second row is transit, is just impact, whatever. and the sustained live load, like a floor load, and then did you see the horizontal time during the life of your building or your structure? And the slow load during the season, the daily, weekly, and summer there's no snow. And earthquake is only happen second. I don't know how many times. I want to pay attention to the wind load. The wind load will be happening multiple times. And the climate change, we're going to change your depth distribution. How we're going to see the frequency-wise, intensity-wise will be the difference. Since that is things we need to look at is how to do the load computation. Currently, when you remember as structural engineer, you know the load compilation. The first one is 1.4 dead load, nothing other thing. And the rest of them is 1.2 dead load plus 1.6 some live load. And we call the live load, if the primary load we come in the consideration is going to 1.6, and other one will be a smaller one. If a snow load, we'll probably go to snow 1.6 snow load plus 1 the live load. That's the primary load component. That's the equation at the bottom we talked about. It's all the reliability based. You do not have to understand it, but just have some knowledge how we can come up the load factors. Now we move into the effect of climate change of the non-stationary. So for the storm surge, the non-stationary, I said, is historic data cannot apply for the future. You must be relied on the model, either physical model for the climate change model and statistical model for the climate change model. Also is regional, localized. You don't use the global one. Global one, they have very big scale, 100 kilometer, the miles, the 10 miles is great. That's not going to apply to our structural design code. I don't go to the detail. Actually, just try to mention out the storm intensity is the function of the sea surface temperature, because we assume a sea level, temperature increase in the next 100 years. Right now is 2 degrees. Certified now the sea level will be affect your storm intensity and the frequency. And also spatial variation is a different island. When we talk about the Pacific, the island, the difference, I have some plot I'm not going to present here because it's not my work, it's somebody the reference. You see the different island, different things, the frequency-wise, the intensity-wise, it's going to be different. Now, we move to see how we're going to model this non-stationary stuff, extreme value. So, extreme value analysis is kind of powerful, very powerful tool to deal with this, what we talk about. First question is which data we talk about, and which data, extreme value. We have 2 methodologies. Is one called the block maximum, annually, daily, or the monthly. Did you see year 1? We just take 1 maximum. Doesn't count other things. And the year 2, and just 3 number. Another methodology called the peak over threshold. We give the dash time, anything above it, we count. So this will maybe have the multiple, the number from 1 year and the 0 number for another year. Doesn't matter. And anyway, these are 2 methodologies how you get the data. This comes from the CBROC, the project 2005, copy from those. This is the basic step. Now the function, the probability function that calls the generalized extreme value GEFV is standard. If you go to the probability class, you do that. This particular function has the 3 parameter control. Normal distribution, not normal distribution, only have the 2, mean value and standard deviation. This particular has 3. One is locator, which means where is the center. And another one is a scale parameter. This 2 is similar like a normal distribution you are familiar with. We have mean values like a locator, all those things. And the scale value like the standard deviation, like a scale, how narrow, how broad, was uncertainty we'll talk about. And the particular one for this shape function, shape parameter determine the uptail distribution. keeping in mind, we talk about the extreme value. Extreme value is tail behavior. It's extremely difficult to get this tail behavior correct. Even we have the data, I have experience with the structural health monitoring, I monitor breach data. Never get the tail right because the reason you use a different distribution always can feed the data you have, but the tail difference behavior totally different. We don't know which one is right, even we have the data. So the value of data, we have to be careful. We just say we have a lot of data. Usually extremists don't have data. There's very few data we talk about. So this is a general equation. When you have the xi, that value less than the 0 is a Weibull distribution. People probably familiar if you notice. Equals 0 combo. That's two very common distribution we're doing with. Now, what are we going to do about the non-stationary? It's right now the current methodology is very simple. Put your location number as a function of your time, a function of the temperature. You make a variable. So this is the report. They like a locate function is consider the different seasonal difference, tidal cycle, or different location long term, climb variability. It's all a bunch of these things, and the scale factor as well. Because control your central point and the broad disperse the side. It's two important things. However, the shape function is keep the constant. Is that true or not true? We don't know. We don't have the extreme tail behavior. Right now, so far, it's constant and also it's negative. So that was the full distribution. Okay? So once you put this, you will have to, you can do the deal with non-data. I don't talk about the details about this. And then you talk about C surface that is also part of the foundation. Okay, resilience, now we just talk about resilience and mitigation. For the piers, I just give you an example. We can permanently relocate this pier because sea level rise. And or increase the pier depth, or increase 2 feet, 3 feet, no big deal. I'll talk about next slide. And also, we do some structurally smart idea. I will show you next slide as well. And uplift force will be through your search. The second step we talk about, of course, we do the life cycle cost analysis optimization. This is very standard. If you do the maintenance every 5-10 years, and what's the cost of that? It's very general things. It's not practical right now. I will make a conclusion about that. By the way, this very new concept is decision making. Right now should be shift from predict then act to scenario based, because we talk about extreme scenario. Which one we include, which one not include, how we're going to do that. That's example I will tell you. Resilience mitigation. The first one, people think raise the deck. Yeah, that's one more slide. Yeah, risk deck is nothing. Actually, it costs a lot of money. The shipyard say if you reduce the 6 inches, I can get $1 million. It's a simple solution, but it costs money. The next one is make a connection. Did you see the damage? This is tsunami damage. This. If we design, keep the pier. Let the deck float up. So we reduce the load from the wave load or wind load. You keep the pier, you can reduce those things. And then redo the deck. That will be much simpler. And another one is uplift force. Include your calculation to resist that. And this one I want to point out, sea level rise may be reduced, or maybe do the good things, because your water, the clear space is shallow, then you do that. And it's better. So not, once again, climate change will not always do the bad thing, some do the good thing. Depends on what you look at. So this, I think, last slide summary. So extreme analysis is a powerful tool to deal with non-steering. That's what people are using. I'm not getting into the detail which is the particular one. And 2 of 3 parameters will be time variant dependent, and to deal with these things, how accurate, I don't know. And the SST, the surface, the sea surface temperature also can be include to quantify this scenario, the non-stage error. Once again, regional local things is extremely important. Otherwise, you mess up. You can get a number. Number will be reflect what you have. Then once again, SC7 will got new things come out in the 2025 and 2028 in that we follow as a ACI 348. I'm sure that I will follow with the kind of connection I'm working with. So finally, this last infrastructure resilience planning should be based on the life cycle cost. Of course, everybody understand that, but it's very difficult to quantify this. With structural design or design, we have to specify the number of load combination. This infrastructure resilience planning is very difficult. I asked the people around it, people do their own way. Some top level people, they say they think we can do it. In reality, no people, because your goal is different, your time frame is different, everything is different. I think this is very general things. Thank you very much for any